Hello, this is your concrete path. In the previous lecture, we have the concepts of shear force and bending moment, and the derivation and all that stuff behind those shear forces and bending moments. Today, we would be purely going through the derivation, through the problems of your shear force and bending moment. Let's take the problem number one. Problem one, we have we have a say we have a beam. This is your determinate beam, cantilever beam. You apply a load, a concentrated point load at the free end of the beam. Say your beam is length of length L. Now you need to calculate. You need to get the shear force diagram and your bending moment diagram. One basic method from which you can solve is that get the reactions. Say if you say that the cantilever it has three reactions to offer: reaction in x, reaction in y, and moment in about z. So if you calculate that summation fx goes to 0, we can say that your horizontal reaction of the fixed support is 0. And if you say that summation fy goes to 0, we can have that your reaction at a, say this is your support a, you can say that that reaction at a, that shear force at a, or reaction at a, is upwards plus your minus p acting downwards here equals to 0. So your reaction at a equals to the load p. Now if you want to say that that summation of moments at point a about the z-axis, we have that equals to 0. Then we have the clockwise moments as positive. Then we can solve that p into l clockwise plus m into z minus anti-clockwise equals to 0. So your moment z equals to p into l. Positive means here that the assumed direction is correct. Assumed direction is correct. That's anti-clockwise. So if you want to say, so what is the shear force diagram? We can say uh, that let's this is your reference line. Now we have the reaction at A. We have the reaction at A equals to P. If you want to say what is the reaction at the end, say this was your support here. The reaction at A was equals to the load P, and your moment was here m into that was moment was equals to m p into L. So if I want to say that what is the shear force at the point itself, so if we cut the section just we at dx almost tending to 0, we can say that say this is your small dx zoomed zoomed in, that you have there you have the reaction at a equals to b, and say this dx equals to very it tends to 0. We can say here some shear force is there. So if we say that the uh, what is the shear force here, we can say shear force at a equals to that p. So your shear force is upwards equals to p. So your a straight vertical line of p is here as a shear force. So then we have that in this region there is no external load. So since there is no external load, since there is no loading intensity in the length L, we have that if this is 0, we can have that V equals to constant. So your shear force would remain constant. So we can go straight up to the point just to the left of the left of P. Now we can say that at point load this condition is not valid. We can use the other condition that uh, that uh, that change in shear force equals to minus of P. Then the shear force at the free end, we can say, equals to shear force at the just to the left of point load P minus minus of P. So shear force just to the left of P was your positive P, and this minus P equals 0. So your shear force at the end is 0. We can have this arrow, we can say that shear force has dropped by amount of this load P. So your shear force diagram is a constant rectangular diagram. So for the bending moment diagram, we can have that this is your reference line. Since the moment at A, we have that uh, P into L, but it is anti-clockwise. So we have that the if this is a section, if moment is acting uh, this clockwise, we can keep it as a positive. But here the moment in the left side is anti-clockwise, we can have that negative value of bending moment. So your moment here is P into L minus. So we can say that we only have that two critical points. One is the point of this support A, next one is the point of this point load P. So we have only two critical points. We can say we have only two critical points. This is the that very important statement that we can have in order to get the that things very become easy. We can say that between critical points between critical points, there is no sudden change. There is no sudden change or in SFD and BMD. So if you have n number of critical points in SFD, you might have n, or you might have n, or you might have say n plus 1 or anything. The n plus 1, we can say I number of critical points in BMD. That I, we can say that the number of I equals to the number of times your shear force diagram changes the sign, or shear force becomes 0, sign shear force change sign, or V becomes equals to 0. At that point we can have one more condition for bending moment, one more critical point for bending moment. So for this condition, there is no change in that. There is no shear force where there is no section where shear force is 0. We only have two critical points for bending moment also. So here it was the one critical point, this one was also one critical point, then the line was straight. Here two critical points, you have to join them. But how can we join them? If say that that the if we have that shear force diagram of degree x to power 1, we have the degree of here the degree is that straight, it does not depend on the value of x. So we can say it's a function of x power 0. So your bending moment diagram would be a function of x power 1. So it's linearly varying. So we have to connect to the two critical points by a straight line. So this is your bending moment diagram. So the bending moment diagram here is that negative bending moment diagram. So it's hogging bending moment. So if you want to make the deflected shape, we can have that. This was your fixed support. This was your reference line. This was your reference line initially where the point that beam was. Then you had the kind of, we can have uh say let's say it's your beam from this side is fixed. Now if you are applying load of p kilonewton at this point, so if you apply load, it would get deflected by this in this fashion. So your bending moment diagram is hogging, so your that deflected shape is also in a reference that we can say that the deflected shape is kind of hogging diagram. For the fixed point, we have that theta should be equals to 0. Here the theta of the deflected shape should be 0. Then we have that curve off this way. Since moment at every section, we have that here at every section there is a moment acting. There is a moment acting. So we can say that we can have curvature. This is a curvature 1 by r. So there is curvature in the beam. There's no part where it is straight line. So there is a curvature in the beam. So the, this is a hogging this one hogging bending moment, or we can say this is called as deflected shape. So your deflected shape would be like this. So uh, so if you want to say what that for the hogging moment, if we have 2 points, if you take any 2 points, then you connected them by a straight line. If you connected them by a straight line, that if the straight line is below your curve, if straight line is below the curve, we say the it's hogging moment. Let's take one more problem. We have next one, that this is your fixed support. You are applying a moment equals m at the free end. You need to calculate shear force diagrams and bending moment diagram. Uh, See, in this question, in the previous question, we could have also solved this question by other method. Say this was your load P. If we cut a section at say any x, so here the shear force was say Vx upwards, and bending moment was mx. So we can also solve this shear force diagram and bending moment diagram this way, that say we can say summation fy goes to 0. So your that we can have p minus p plus shear force at x equals to 0. So shear force at x equals to p. uh, so we can have that at v equals to 0, at when x was your 0, your shear force was equals to p. When your when your mm, when your x was equals to total length L, your shear force was also equals to p. So if you have the diagram that at every from 0 to L, if it is your 0, it is your L. From 0 to L, your shear force remain constant value of positive p. So this was your shear force diagram. Next one is your, if you say summation mz equals to 0 at this section, so we can say that, or we can say summation f mx goes to 0. We can have that clockwise of p into x and plus m into x equals to 0. So your bending moment at x equals to minus times of px. That means the moment is acting anti-clockwise direction, but we assume that the direction is clockwise direction, so we have that minus px. So if we plot the variation, that if you have a straight line, if you have a reference line of this one, we can have that moment at x equals to 0 equals to 0, moment at x equals to L equals to minus of PL. So we have here 0, we have here minus PL. So we can connect them by a straight line. Because why straight line? We can clearly see from the equation that moment at x equals minus times b into x power 1. So your function moment mx is a function of x power 1. So that's linear, or we can say 1 degree. Similarly, for the shear force, we were having that vx equals to p. That we can also say that p into x power 0. So your shear force is independent of that variation in x. So your p remains constant. Now we can have that next question, that you are applying an anti-clockwise moment at the free end of moment of m. We can have we can also say that for the easy calculation, that let's take this part. We can have moment at this one is your moment m. Let's take any section x. Say this is your section x. We can have their shear force at x equals to this one, and moment here is mx. We can say that summation fy goes to 0. Then we can have that uh, uh, that since that we can say that there's only one vertical force acting, that shear force, that's equals to 0 plus 0 plus 0 equals to 0. So your shear force diagram would look like this one. This is your shear force diagram for the entire length. Then we have that summation mz, summation at x, summation of moments at x equals to 0. We can say that minus m acting anti-clockwise direction plus moment at x acting clockwise direction equals to 0. So your moment direction is positive. That means assumed correct direction is positive. That is, your moment is acting clockwise at every x. So at moment, so moment at moment at x equals to 0 equals to moment, and moment at x equals to L equals to moment m. So your moment diagram would look like that positive moment diagram at every at at every at every section of x. So bending moment diagram is like positive value of m. So it's like that you are applying a moment of m here, and you're resisting this by an equivalent moment m. So your bending moment diagram is like this. So you are saying that that sign convention also, that it is a sagging bending moment diagram. It's your sagging bending moment diagram. So the beam is happy. So if you want to make the deflected shape, so you're applying two moments at here. So beam would deflect downwards, but beam would deflect it this way. So actually, if you are having a simply support beam, say this was your simply support beam, then you applied a moment m here. So it would have deflected that this way, a sagging bending moment diagram, because that at the two ends it was not able to move upwards or downwards. So the deflected shape was, say, downwards. But in this part here, it can't go upwards or downwards. Then if you apply a moment m, say if you apply a moment of this side, from this side is your fixed beam. So if you apply moment m uh, acting anti-clockwise direction in this direction, in this free end. So if you apply moment m, so your deflected shape would look like that, this way. We can say it's a sagging bending moment. That sagging bending moment, because of that sagging bending moment, you can have deflected shape of that. Here the slope should be 0. So your deflected shape would look like this one. And uh, uh, that sign convention is that say you take two points anywhere on the curve, you join them by a straight line. If the straight line is above the deflected curve, above the curve, we have that sagging shape. We can say that it's your deflected curve, or we can say deflected shape. Now next one, you have beam. You have a beam of that. You have a beam of, say, fixed beam, and UDL is acting entire length with the intensity of W kilonewton per meter. So if you take a section at x from x if you take a section x at x from your free end, you can calculate that. You don't need to get the reactions also. This is very like uh, that smart approach, because you don't need to calculate the reactions also. So we can say at x, your shear force acting here is Vx, and your that bending moment at x equals to mx, and your external loading was your W kilonewton per meter, and here there is no load, so we can say summation m summation m summation Fy goes to 0. So your shear force is acting upwards, and your loading intensity downwards. So we can say the area of the that loading diagram. This is your loading diagram, W into x equals to 0. So we can say shear force at every x equals to W into x. So your if you say that what is the shear force at x equals to 0, we say that this is your x equals to 0. We say that shear force at x equals to 0 equals to 0, and shear force at x equals to length L equals to W into L. So your variation of the shear force is x to power 1. So if you between the two critical points, there is no sharp turn possible. So here the shear force was 0, and here the shear force is positive positive W into L. So your positive W into L, positive W into L. So if we have to join the two, we can have that. This is your, if you join the two, it has to be joined by a straight line, linear line. We can say 1 degree curve, or linear. We write it as linear. So what is the slope of that line? What is the slope? Tangent of theta. What is the slope here? We have the equation that uh, dv by dx equals to loading intensity positive. If the loading intensity was upwards when we derive the equation, we have that uh, we have that loading intensity we kept as upwards. Then we got this relation as positive, but the loading is acting downwards here. So your slope of the shear force diagram is minus times W for this case. So your slope is minus times W, loading intensity. Now next one is your summation of bending moments about x. Summation of, we can say summation of that, not bending moments, we can say summation of moments at x uh, equals to 0. So we have that we can say your summation of moments at x equals to 0. So your say this is your UDL of length x. It's acting, say it's a centroid of the load acts at the centroid of the at the mid of that x by x value. So your net, you can treat that equivalent load of that UDL acts at this point with a total load of equals to W into x, W kilonewton per meter into your x meter. So it becomes your W into x kilonewton. So this load acts at, say, this was your x at x by 2 from your section while you cut the section. So you can treat it in this way. We can say that your moment x is here mx vx. So we say that W into x acting at x by 2, it's clockwise, plus moment x is also clockwise. So your moment x is actually anti-clockwise direction, minus wx squared by 2. So your moment x is a function of x square. So it's a parabolic variation. So your bending moment diagram is a parabolic variation of wx square by 2. So if you say what's the value of a moment at x equals to 0, that's equals to 0. Moment at x equals to L equals your minus times WL square upon 2. So your moment diagram is here. It is this was your shear force diagram. This is your bending moment diagram. So your shear force at x equals to 0 equals to 0, and your bending moment here is WL square by 2 negative. If you have to connect the two, what was the variation? That was your parabolic x square. So your variation is parabolic. You need to just get the value of critical points. There is no sharp turn possible between the two critical points. Once you got the two critical points, you say that how should we connect to them? Either we should connect them by a straight line, we should connect to them by a horizontal line, we should connect to them by a deflected that curve. Is it 2 degree? Is it 3 degree? We can get that. So let's have that we have the parabolic variation. But should I go this way or should I go this way? Let's say we have that equation dm by dx equals to shear force. So slope of the bending moment diagram equals to the shear force at that point. See here the shear force is W into L. So your shear force is there. If your shear force is there and that's also positive, that means your deflected shape there should be. That means yeah, that you have to connect the 2 points by a line which is having some slope. You can't go straight. You can't go here that theta equals to 0. You should go size that here there should be some theta. If you are going by this curve, here is not that theta. But if you are going this by this curve, there's getting a theta developed. Theta. Okay. Oh, so if you are joining the now you have to join the 2 points. See, it's getting out of the track. We need to adjust that curve. See here the theta, it has to be that tan theta or slope, it has to be equals to 0. Why? Because the shear force diagram here is 0 because V free. Because here the shear force is free, we can say that tan theta equals to 0 equals to your slope at this point equals to shear force at this point, that equals to 0. So this curve is not possible. And if also you are going by this curve, you will see how you can connect the 2 points. If you are going by this curve, here there was some theta, but it's not true. So this curve is not possible. So you can remove this part. Then you have that here the tan theta equals to your shear force at this section, that's equals to W into L. So this curve also your deflected shape would be like say here this theta is 0, then we have the deflected shape of hogging nature. Next one is your that cantilever beam with a uniformly varying load with a uniformly varying load of with a peak of W at the at the at the cantilever end and 0 at the free end. Say length is your L, intensity of say loading intensity at the cantilever end is your W kilonewton meter, and it decreases downwards up to the point that W equals to 0. So let's take a section here. You can say let's take a section at X from that free end. We can have loading downwards. Suppose the shear force here is V into X. Vx, and moment here is moment x. Let's have that summation Fy goes to 0. We can have that shear force acting upwards, Vx, plus your loading acts downwards. So uh, if this is your loading diagram, you can say what is the total load. This was your W kilonewton per meter. So your loading becomes that loading becomes in terms of kilonewton. We can say this was your small w. We can write total W equals to area of the that loading diagram, 1/2 W kilonewton per meter into L meter equals to 1/2 WL. So your loading diagram acts like this. So we say that it's acting at the centroid. Say it's your centroid at distance L/3 from this point. So what should be the actually we are cutting the that that beam at x from A. Say here it's the x. What should be the value of this intensity here? We can say that intensity at x equals to we say that W kilonewton per meter was at the free end, so it's varying per unit length of L. If we want to get it for this triangle, we can say that by similar triangles that equals that Wx by L. So your intensity here is Wx by L. So if you are saying that what should be the summation of forces, we say that area of the this is your area of the that loading diagram. So W is acting downwards, we can say minus Wx by L, and acting for a distance of for a length of x equals to 0. So your shear force at x equals to half of Wx square by L. So your variation of the shear force is a parabolic variation, a parabolic 2-degree variation. So let's say shear force at V equals to 0 shear force at V equals to L, shear force at x equals to L equals to half of WL by 2, WL, yeah, WL by 2. So your that WL by 2, it's positive. This is also that reaction at A. This is also called at the reaction at A, vertical reaction at A. So if you have that shear force diagram, you can plot the shear force diagram. Say this is your reference axis. So the shear force here is 0. Shear force here is positive WL by 2. WL by 2. You need to connect the 2 points by a parabolic curve. So there is no straight line. The line should be the variation should be by a curve. So the curve should be either this way, or the curve should be either this way. We should now check which curve is okay here. Say we have that dV by dx equals to that loading intensity. If the loading intensity is downwards, since the loading intensity at this point is acting downwards, so your that dV by dx equals to minus times that. So your slope of the curve is your negative minus W. So your slope of the curve is downwards. So it's your slope minus W slope. So now the curve you got, you have to connect the 2 points. Here the slope has to be 0. Here the slope is 0 because shear force is 0. Now because that loading intensity is 0. So this is your shear force diagram, positive. Now coming back to the bending moment, let's make a bending moment equation for this beam. We have that let the centroid of this triangular variation act as at here. This is your x by 3. So we can say summation of moments at x equals to 0. Then we say that clockwise moment of mx, and your vx acting at 0, so shear force effect is not there. We have that, and then clockwise moment of area of that triangle is your half of that W x by L into x. This value of load acts at x by 3 from your section equals to 0. So your moment at x equals to minus times, that means your moment is acting anti-clockwise direction. So your moment is mx equals to minus times that wx cube by 6l. So your moment at x equals to 0 is equals to 0. Moment at x equals to l equals to minus times w l squared by 6. That's also called as moment at a. So if you want to make the bending moment diagram, we have that. This is your, so that the two critical points are here. Here the moment is 0. Here the moment is wl squared by 6 negative. You need to connect the 2 points by a that x cube. We can say degree is 3. Here the degree is 2 parabolic. Here the variation is cubic. But the question is, how should we connect them? Either this way or this way. Since the dm by dx equals to shear force, so the slope here should be equals to the shear force at this section. Shear force at this section is positive WL by 2. So your shear force diagram has to be that WL by 2 tan theta or slope. This is positive. So your curve is acting upwards. If your curve is this way, you need to connect to the 2 points. That the possibility here is, since the shear force here is 0, the slope has to be 0. So we can say, we can connect the 2 by this one. It is a cubic variation. Next one is your let's say it's your beam. Wait, we will get one more question. Say this is your fixed beam, that cantilever beam of length 5 meter. Now the thing is, we have tapered it, say this way. Now the loadings are 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. 5 kilonewton, 5 kilonewton, 5 kilonewton, 5 kilonewton, 5 kilonewton. 1, 2, 3, 4, 5. But the total length is 1 meter, 1 meter, 1 meter, 1 meter, 1 meter. Total length of 5 meter, and a moment of 20 clockwise acting here. Now we have a section. We have a section at x equals to 2. This is your 1 meter. This is your 2 meter. So at x equals to 2, we have 1 point just left of that 2 meter and just right of that 2 meter. Say this is your point D and this is your point C. We need to calculate shear force at C and bending moment at C. Shear force at D, bending moment at D. So for that, if we say that, what is the shear force? Shear force is the summation of all transverse forces. Either we can go from the left side or we can go from the right side. If we go from the left side, you have to calculate the reactions first. Now, if you calculate it from the right side, left side, you need to get the reaction first. If you don't want to calculate the reactions, we can directly go from that right side also. So we can say, for the reaction C, for the shear force at C, cut that section. Let's take this section. So this tapering does not make any difference if we keep it as a line. Say here the load is acting 5, and load is acting 5 kilonewton, load is acting 5 kilonewton. So you are cutting just before C. Say this is your point C, that point C. So your shear force here, let's take shear force here equals to VC, and moment here is moment MC. Then we have also 20 kilonewton meter acting upwards, that clockwise. Let's say this is your 1 meter, that this is your 1 meter and this is your 1 meter. We can have that summation equation of static equilibrium, that Fy goes to 0. Then we have Vc upwards, and there minus 15 acting downwards equals to 0. So your shear force at C equals 15 kilonewton. Now if you want to say that what is the moment at C, we can say that moment at summation of moments at C equals to 0. Then we have that bending moment at C clockwise, and the effect of all those are also clockwise. So your this is 5 into 1, and the next one is your 5 into 2 meter plus 5 into 3 meter, and your plus 20 clockwise equals to 0. So your moment at C equals to minus times 30, 15, that 15, 40, 50, that is minus 50 kilonewton meter. Now if you want to say what is the shear force and bending moment at section D, so we have to calculate that if you cut the section at this point, say section D, we want to check the effect of this point, that 5 kilonewton load of that concentrated load. What is the variation? We are not saying D is very far from this load. We are saying just to the left and right. We want to check the variation. So if you have this point section D, we have that, let's say here the shear force is shear force Vd, and moment here is bending moment D. Let's have that section D. Then your loading is 5 kilonewton here, and a 20 kilonewton clockwise moment, and 5 here, and a 5 also here, 5 kilonewton. Now we want to check the effect of this point also, this point in concentrated load. So this was your 1 meter length, this was your 1 meter and 1 meter. Let's go summation Fy goes to 0. Let's say that Vd upwards minus 15 equals to 0. Is it minus 15? No, it's there is one more load also there. Minus 15 and minus 5 equals to 0. Say your shear force at D equals to 20 kilonewton upwards. And let's say summation of moments at D equals to 0. So your bending moment at D clockwise plus that the effect of all those loads. See the effect of this one into that small dx equals to 0. So we can write it 5 into 0 plus that the extra part which we already calculated, that was the same, that effect of 5 into 1 plus 2 plus 3 plus 20 equals to 0. So your moment at D is also minus 50 kilonewton meter. So the conclusion is that because of that point load, or because of point load, there is change in shear force, or we can say shear force diagram. In the shear force diagram there would be a change because of that point load. So we can say sudden rise or drop. So in our case, that 5 kilonewton rise from, if you go from C to D, so rise or drop in the SFD, but there is no change in bending moment or bending moment diagram at either you cut section just before or just after that there is no change in bending moment value. That's also that minus 50. That was also minus 50 from this side also and from this side also. But there might be, we know that there might be a change in slope because of point load. There might be a kink is possible. The change in slope is possible there, but we don't have to draw the shear force diagram for now. Next one is your a simply supported beam of length 9 meter. Say this is your support A and your support B. Now the that loading intensity is such that here the intensity is 9, that 10 kilonewton per meter, and the intensity here is 30 kilonewton per meter. We need to calculate, get the bending moment and shear force at distance x from A. Suppose this is your x. We need to calculate the get shear force and bending moment at x from A. So it's saying that get the equation of shear force and bending moment. Then if we plot it from x equals to 0 to 9, we can get the shear force diagram and bending moment diagram. We can divide the loading into two parts. One is your a rectangular portion with an intensity of 10 kilonewton per meter. So this is your 10 kilonewton per meter. Next one is your 20 kilonewton per meter. So the centroid of this rectangle will be acting at say 9 by 2 from any of the supports, and the centroid of this triangular variation would be acting here. So we can get the reaction. So because it is saying the shear force and bending moment diagram at x from A, we can say, let's say this was your support. Let's say the support gives a reaction of vertical reaction of A, and the beam has been cut at x from A. Suppose the shear force at x is equals to Vx and moment here is Mx. Then the variation of loading is this way. This is your 10 kilonewton per meter, and it varies to a point that this is your Wx. This is your Wx, and we have that shear force at x equals to, this is your shear force at x equals to Vx. So your variation is downwards. Centroid of this one, centroid of this one. We have that if say if you cut at any x, at least you will get an intensity of 10 kilonewton per meter. So we are not worried about that part. For the triangular variation, we can have that what is the value of Wx, W at any x. We can say W at any x equals to that triangular part was your 20 kilonewton per meter. So it changed from 0 to 20 kilonewton per meter in 9 meter length. So if you need that loading intensity for x meter of that triangle, we can get the shear force, that loading intensity variation as 20 by 9 of x. So we can say this was your length x. We can say summation Fy goes to 0. So your reaction at A, but firstly we need to get the reaction at A, then accordingly we can get the shear force at A, because there are two unknowns. For that we need to get the shear force, that reaction at A. So we can say that summation Fy goes to 0. These are your reactions. Summation Fy goes to 0, so we can say A plus B equals to 10 kilonewton per meter into length 9 plus that half of area of that triangle, 20 kilonewton per meter, into your 9 meter length. So your next one is your summation M. Let's take any point, because our unknown is because for our analysis we need the reaction A. We can say that summation moment B equals to 0. Then we can have A into 9 clockwise. We have assumed that reaction is upwards. A into 9, that minus that 10 wx squared by 2, wx squared by 2, and that minus area of that triangle 20 into 9, acting at x by 3 from your support B equals to 0. So your that shear force, that reaction at A comes out to be equals to 75 kilonewton. 75 kilonewton. Let's take the value of A equals to 75 kilonewton. Then we can say that 75 kilonewton upwards plus that shear force is also acting upwards, and we have that loading downwards equals to that minus 10 into length is your x, and minus half of that triangle area. We say that half of that the intensity here is wx total, but yeah, see the error here is we got the variation for the triangular part. This is for the triangular part. This is for the triangular part, that wx. So there is also a rectangular part here. So that let's erase this. So this was your wx, and here is also 10 kilonewton. So we have that 1 by 2 wx, and acting for a length of x equals to 0. We have that 75 plus 75 minus 10x minus your wx is the value of wx was 20 by 9 of x. 20 by 9 of x into 1 by 2 into x equals to 0, equals to minus let's take plus v shear force x equals to 0. So your shear force equation becomes that 75 minus 10x minus 10 x squared by 9. So by knowing the shear force variation, by plotting for different values of x, we can get the shear force diagram. Similarly, now going for that moment at x, let's take summation of moments at x goes to 0. So the see, x is from A, so your reaction at A equals to 75. So we can have that clockwise of 75 into x plus we have minus loading intensity was your, for the rectangular part UDL, we have that 10x squared by 2, 10x squared by 2, and for the triangular part we have that area of that triangle equals to w into x, half of that wx. Your wx was 20 by 9 of x, and your length is x. So this load is acting at a distance of from that section x, but at a distance of, say, this is your x by 3, acting at x by 3, and the moment here was, we assumed that anti-clockwise moment of mx. So your moment is a minus mx equals to 0. So your bending moment equation at x equals to that 75x minus 5x squared minus 10x cubed by 27. We can if we, by knowing the values of x, we can plot the variation for your bending moment diagram. Now let's take the next question, that let's take the new question that you have simply support beam. Yeah, simply support beam. Let's say this one, a load P acting at a distance of A from support A, and a distance of B from support B, say such that A plus B equals to length L. We need to calculate the shear force diagrams and bending moment diagrams. So let's say that summation, we need to get the we have to get the reactions first. We say that summation Fy equals to 0. So your reaction at A, vertical reaction at A, plus reaction at B equals to load P. So you see, if the reaction is acting upwards, we can say A plus B equals to P, and by summation of moments at, take any, let's take moment at B equals to 0, we can have, which implies that A into, let's take A plus B equals to L. So your moment equals A into L clockwise, and your minus minus P into B equals to 0. So this one is your clockwise, this one is your anti-clockwise. So your reaction at A becomes PB upon L. So your what is the reaction B? We can say that P minus PB upon L, that's equals to P L minus B upon L. So your reaction at B equals to PA by L. So the reaction, suppose if the if the if the A if the A and B are equal, say A equals to B equals to L by 2, we can get that reaction, both reactions A and B equals to B by 2 from the equation. So for the short way, we can say, if for the reaction A, it would be that P and the distance on the opposite side, that is your B upon total L, and for this one, P into opposite side distance, that this one A L by that L for distance from A. Okay, now we have to get the shear force and bending moment diagrams. Let's say, let's take that we can have that, we can cut the sections, or we can directly create the equation, that diagram. Let's take that, let's take at any x, say in the region x, in the region AP. Let's take this region firstly. In the region AP, we can have that section. Say here this reaction is A, and we have got the section just before, just before, say just before. If you have that section just before, the effect of P won't be there. The effect of P won't be there. So let's say that shear force here is Vx and moment here is Mx. Let's say that, let's say the shear force here is Vx and moment here is Mx. Then we can have that we can say that the length is A. It doesn't matter. Or we can cut at any x. We know that the variation would be linear. We can do directly, or we can say we can vary the x. Let's vary the x to get a better view. Let's vary the x. Let's say you have cut the section in the region AP at anywhere. We don't want to write just before. We would say at any x. We can add here that, we can also add here that just before P, but at x anywhere, but it should be just before your load P. So if we cut at any x, but the effect of P is not there. So we can have that shear force, that summation Fy goes to 0. We can say A plus A minus Vx equals to 0. So your shear force at any x equals to value of A. So if we want to say that at x equals to 0, your shear force was equals to A. That was your Pb by L. And 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 for the x equals to value of A, we also have shear force equals to A, that's equals to Pb by L. So your variation of shear force along the line length just before A comes out to be a straight line with a value of Pb by L and a constant value. We can also say that dV by dx equals to loading intensity. Since in this A region there is no loading intensity, so your shear force would be a constant value. So your shear force is a constant value of P B by L. So it was your just before load P. Now we can have the effect of P also in this. Now firstly we can also get the moment summation of moment at summation of moments at x equals to 0. We can say A into x clockwise, and your minus times moment at x equals to 0. So your moment x becomes A into x. So your A was your Pb by L into x. So we can plot the variation of bending moment also. Bending moment at x equals to this one. Let's say moment at x equals to 0 equals to 0. Moment at x equals to A equals to PAB by L. PAB by L. So your variation of bending moment diagram is like positive value of PAB by L. Say the value of bending moment here is 0, and the bending moment here is positive value of PA. Let's say here PAB by L. Then we have to join them. We know that if SFD variation is that it is a horizontal line, then the so its variation is x power 0 degree curve. Then the bending moment diagram is n plus 1. Say degree is n plus 2. Say if it is n plus 1, here it is n plus 2. So your variation is linear. We need to connect to the 2 by a straight line. This is 1 degree curve, and the slope here is the value of shear force at this. We can say tan theta equals to your Pb by L. Then for the next part, we can get the value. Say now we can cut the section. Say this was your reaction at A. Now we can say for the section between PB, we can cut at any section. We can cut at any x, that any x from A, such that it cuts in the region PB region. In this region we want to calculate the effect. So the effect of loading P is also included in the calculations. So your say the load P acts at here, and the maximum say it goes to point B, but we cut the section at say x from A. This length was your length A. So we can get the value. Say the shear force here is downwards. We can assume shear force here is downwards Vx, and the moment here is moment Mx. Then calculate the values of shear. We say that summation Fy goes to 0, summation Fy goes to 0. Then we can write A. What's the value of A? A is your Pb by L, and then upwards then minus P, then downwards minus Vx equals to 0. So your shear force at x equals to Pb minus L by L. So your shear force becomes minus times P by L. What's the value of L minus B? L minus B is your value of A. So your L minus B is your value of A. So this value shear force at x equals to minus pa by l. What is the value of shear force at, say, x equals to 0? Let's say we have to calculate the value of shear force. If you want to say that what is the effect of uh, this means that this is the it has touched the concept of that another topic from structural analysis, that influence line diagram, but we don't have to do that for now. That if you say that what is the value of shear force at x equals to 0, that comes out to be 0. That when if you cut the section here, the effect of that uh, let's remove this part. It might be confusing for now. We need to calculate when the x was your when your x was uh, we need to calculate the effect in the region PB. For that, the value we had to vary from this after a to that point. Say this one is your x minus a. Yeah. For your Vx, shear force at x equals to, let's say, shear force at x equals to a. When we cut the section such that we include the effect of p also in the equation, since we got the equation in terms of p also. Now if we want to say what is the value of shear force at when x was just equals to p, we want to say what's the value that is equals to minus p a by l, negative minus p a by l. And what is the value of shear force when x is going from that a, it has crossed the a, now it reaches to end point, that's your point b. So this distance was your b. So your if the x equals to if x equals to that a already gets reached, then a plus b, that's equals to l. So if x equals to l, we can say shear force at l equals to minus pa by l. So it's also a constant value of minus pa by l. Now if you want to plot it, we say that a value of minus pa by l from when it was just before and just after, there is a minus pa by l, negative value of minus pa by l, negative value minus pa by l. Then it's a constant value till it reaches point b. So it's all this value is also minus pa by l. Then we know that because of that, the effective dv equals to minus p, because of the point load here acting at this section. We had that shear force at, say, this one is your shear force downwards equals shear force upwards minus p. So shear force downwards we can calculate. This one was your shear force upward. We can say shear force that shear force downwards equals to shear force upwards was pb by l. This was your positive value of pb by l, minus times p, we can get p pa by l minus pa by l. So there is a sudden drop of p because of that effect. So your shear force diagram looks like this one. Now if you want to calculate for the, we know that the variation would be a linear variation because the moment here is simply support beam reaction moment. There's no moment there, and then the line would be somewhat this. Let's make still the calculations. Say we can write summation of moments at x equals to 0. So your shear that reaction at a was your pb by l, acting for a distance of acting for a length of that x, value of x clockwise, and the effect of that load p is acting for this distance x minus a, anti-clockwise direction p into x minus a, and your moment is also acting anti-clockwise direction minus mx equals to 0. So your moment at x equals to that pb by l x minus times p x minus a. If you want to say what is the value of moment at point p, that means when when x was a, what is the value of moment at b? We can say moment at when x was equals to 0, when x was equals to a, we can get pb a by l minus p a minus a. That's your pb by l, pb upon l. Now if you want to calculate moment at x equals to that, if x varies from that a, after that it reaches to the point b, so your x equals to l. So that we want to calculate the moment at the end. That's equals to pb l by l minus p l minus a. That's equals to pb minus p. This l minus a is also pb. That's your zero moment. So your variation is pb by l and 0. PAB. Here the value of this also is PABBL. So we got the values, same values by on the both sides of the that section P. So your variation is a variation of linear variation. That this is a linear variation. Both are linear variation. See, in the equation also we got a function of x. The x was varying here. It is a function of x power 1. I hope you understood the problem. Now, so we forgot the that slopes. Want to say what is the slope here? That we know that for this part it was your slope of positive PB by L because the shear force was positive. But for this one, so your slope is that line is acting downwards. So your slope is, we can write tan theta equals minus times P A by L. We have that dm by dx. Slope of that bending moment diagram equals to that shear force at that section. Shear force at that section is your minus times PA by L. Let's have one more problem. Say a simply support beam of length L and a UDL of W kilonewton per meter acting for the entire span. Get the shear force diagram and bending moment diagrams. Let's say firstly we need to get, if it was a cantilever, there was no need to get the reactions. We could have easily solved though. But here the supports, there are two supports. There's no free end. We need to get the reactions first. So let's take that. Let's say this is your support A, this is your support B. It offers a reaction of A, it offers a reaction of B. We know horizontal reaction at A equals to 0. Now we say that summation Fy equals to 0. We can write A plus B equals to UDL acting for length of L. Now summation of moments at we call it, let's take any point. Let's take moment at A equals to 0. We can write about this point. We have that effect of B is anti-clockwise direction B into L minus times plus your clockwise direction. Let's say the centroid is here and the effect is W into L. So your load of W into L acting at a distance of, this is your L by 2 from support A equals to 0. So your shear, that reaction at B equals to WL by 2. We know that we have the concept of that. If you have a symmetric loading, uh, the reactions are, we know that we say that reactions, your bending moment diagram, your deflected shape is also symmetric. All of these are also symmetric, but your shear force diagram is not symmetric. Shear force diagram is not symmetric. Rest all are symmetric, but your shear force diagram is not symmetric. This is valid. This is valid up to the point that if there was no internal hinge, we have not studied the effect of internal hinge as of now. Say if there is no internal hinge, then we can say that for the symmetric loading, reactions, bending moment diagram, deflected shape is also symmetric, but shear force diagram is not symmetric. Let's say uh, that this part of the loading would go to the reaction A, and this part of the loading would go to the reaction B. So we can say this is your W into L divided by 2. This is also WL by 2. Now we need to calculate the that shear force and bending moment diagrams. Say that shear force here is WL by 2. See here you might be confused that this is WL by 2. There is also a load of this W, but it's intensity. This is a load, point load, kilonewton, but this is an intensity. It is a function of length. It's a function of length. Let's say you want to say there is a shear force here. Say here the reaction is WL by 2 kilonewton, but here the loading intensity is W into W kilonewton per meter. Let's say length is 0. What can you say now? So reaction upwards, we can say WL by 2. Say downwards W, but it is into 0. So your reaction becomes that WL by 2, or shear force becomes WL by 2. So we have that variation, that WL by 2 shear force. Then the variation. Then the variation we have to plot. For that, if you want to make the equation also, if you solve it through analytical approach, we say we know the reaction A equals to WL by 2. Let's take any section. Since the loading is continuous, there is no change, there is no point load, there is no concentrated load, or there is no gap of that loading. We have that at any x till it reaches that point B. Let's say this was your x. The loading was W kilonewton per meter. Loading intensity was W kilonewton per meter. Let's say at x, you cut the section at x. Here the shear force is Vx, and the moment here is moment x, bending moment x. Now, if you want to calculate the shear force variation, we say that WL by 2 upwards minus W into x downwards, and minus Vx downwards equals to 0. So your shear force at x becomes WL by 2 minus W into x. So your equation becomes like y equals mx plus c. So your line is decreasing. So your shear force, we can say shear force is decreasing in nature. Shear force is decreasing in nature. Shear force is decreasing in nature by varying the value of x. Say now we want to calculate the shear force at, say, x equals to 0. That is equals to shear force at A, that equals to WL by 2 minus 0, and shear force at x equals to length B, let's say length L. Shear force at length L, that's also called as shear force at B, equals to WL by 2 minus W into L, and which we get as minus WL by 2. Now we want to plot the variation of shear force diagram. Let's say this is your reference line, and the shear force here at A equals to positive WL by 2, and the shear force at the end is minus WL by 2. Here the shear force is minus WL by 2. You need to connect the two lines, the 2 point. Here there are only 2 critical points. You have to connect them by a line that is a function of x power 1, so it's a linear variation. So we can join the two lines by a straight line. So let's say it cuts the that reference line at x from a we can say where it cuts we can get the value. Then we know that at x your shear force becomes 0 at x, or we can say the shear force changes its sign at x from a. So if we substitute the value that at x v at x equals to x, that shear force is 0. So we need to calculate the value of x equals to minus wx. So if we solve it, we can say that x equals to length L by 2. So at the mid span, your shear force becomes 0. So your x equals to length L by 2. Now we need to calculate the bending moment equation. So this was your section. Let's say summation of moments at x equals to 0. We have that WL by 2, a clockwise moment about this point, WL by 2 into x minus UDL of W into x, acting at a distance of x by 2, and your shear force into 0, and then the moment anti-clockwise moment of m into x equals to 0. So your moment x variation is that WL by 2 minus WX squared by 2. So it's a function of x squared. So your bending moment diagram would be a parabolic variation. Parabolic variation. So let's say moment at x equals to 0. That's moment at a. We want to calculate. That's equals to WL by 2 minus yeah, this is WLX by 2 minus WX squared by 2. So it's a function of x. It's a function of x squared. The maximum power is x squared. So we have that WL by 2 into 0 minus WX squared by 2. That's equals to 0. So your bending moment becomes bending moment at the free end at the support A equals to 0, and moment at say x equals to L, that's moment at B, support B, that equals to that WL L by 2 minus WL square by 2, that's equals to 0. So we got 2 points that, see, this is the reference line for bending moment diagram. We got value of bending moment here 0 and bending moment here 0. We can also see from the that supports also that we have two supports. This is your hinged support. It does not offer moment restraint. It allows theta. If it allows theta, there won't be any moment developed. It also does not allow any moment to happen, so it only allows rotation. So once you have that 2 points, then why is the critical point? We know that between the two critical points, there's no sudden change. In the SFD and BMD. But if in the SFD, if in the shear force diagram you have shear force equals to 0, or shear force changes sign, so we got one more critical point in your bending moment diagram. So that's your this critical point. So we got one more critical point at x equals to L by 2. We got some value of bending moment. We want to say what is the value of bending moment at x equals to L by 2. So substituting the value of x equals to L by 2 in your bending moment equation, we can calculate the value of moment at L by 2. We can write as moment at mid, that bending moment at mid, or moment at L by 2 equals to WL by 2 into L by 2 minus W by 2 into L square by 4. That's equals to WL square by 8. Moment at mid span. A positive value of WL by 8. a positive value of WL by 8. So here is that here a value of positive value of WL upon 8. So when we need to calculate that, what should be the variation of the curve? We know that the value that function was a that moment x was a function of x squared. If shear force is a function of x power 1, then the moment bending moment has to be a function of x squared. Then the question is also there that um, what should be the variation, that what should be the slope here? We know that dm by dx equals to shear force. We know that shear force at A equals to WL by 2, positive value. That means your slope is positive, increasing. One statement you can write that in this part of shear force diagram, we have that if shear force diagram is positive, if shear force diagram is positive and decreasing, see, the shear force is positive, but it's getting decreased. The value is getting decreased. So we say that if shear force diagram is positive and decreasing, the slope, the bending moment diagram slope, that's also positive and decreasing. We know that the variation is parabolic variation, that x square. But if we use this, that bending moment slope is positive and increasing. If the slope is some value, that positive value of WL by 2, but this is your slope tan theta. But bending moment is positive and decreasing. How can you decrease a curve when it goes from 0 to say x equals to 0 to say this length L by 2? That means the slope here is maximum, and the slope here is, as we know that shear force, if shear force is 0, that means the slope is also 0 here. At the mid, slope has to be 0. So here the slope is 0. It's parallel to the reference line. So here the slope is 0. Similarly, for this part, it's the same nature because loading is symmetric. Here the slope is that shear force at B. That's tan theta equals to minus times WL by 2. So your maximum moment, this is your bending moment diagram. Maximum moment of WL by 2, positive value WL by 2, WL by 8, WL squared by 8, sorry, WL squared by 8 of at mid span of your length L in the simply supported beam subjected to uniformly distributed load. Hope you understood the problem. Next one. We have one more problem, that assembly supported beam subjected to uniformly varying load of W kilonewton intensity, W kilonewton per meter intensity at support B and 0 at A. The span is of length L. Get the shear force diagram and bending moment diagram. So firstly, we can solve for the reactions. Say the centroid of that intensity, that triangle is here. We can say A plus B summation Fy goes to 0. We can say A plus B equals to area of that triangle, WL by 2, and summation of moments at say any point. Say let's take at let's take at B equals to 0. So we can say that A into L clockwise moment about point B, A into L, and your minus area of that triangle is WL. This becomes your load acting at a distance of say L by 3 from support B equals to 0. So we can write A equals to WL square WL by 6, and similarly we can get B equals to WL by 3, WL by 3 and WL by 6. Yeah, this means that the value of B is greater than the value of A. See, the more close the intensity is towards the one support, that one support will get more reaction. So see, the more amount of load is towards the support B, so your support B reacts more than the support A. So if you want to say that what is the shear force diagram, let's have that reference line for your shear force diagram. Shear force diagram, you can say, let's take any section. Let's take any section that let's take any section. This is your reaction at A equals to WL by 6. We cut a section X from A. Then let's say the shear force here is Vx and moment here is Mx. Then we have the variation that say this is your Wx. This value of Wx, we know that this is W kilonewton per meter per length L, but we need for only X length. Then we can get the variation. Say the centroid acts at this point. We can say that summation Fy goes to 0. We can write WL by 6 plus area of that triangle, the 1 by 2 minus times WL by X into your X. That shear force is downwards plus shear force is also downwards. We can write minus Vx equals to 0. So your shear force at X becomes that WL by 6 minus Wx squared by 2L. So your function shear force is a function of X square. So your shear force variation would be a parabolic variation. Now, let's say shear force at X equals to 0, that means shear force at A. We need to calculate that shear force at A, or shear force at 0 at X equals to 0, that becomes WL by 6. That is the reaction A. So your shear force here becomes WL by 6. And in the at the shear force at, since there are only two critical points, A and B, we can directly say that the shear force at X equals to length L, that becomes equals to WL by 6 minus WL squared by 2L, that becomes WL by 3. That's the shear force, that's the reaction at, but it is actually negative, say minus 2 inverse, that's minus WL by 3. So this is the reaction that minus WL by 3. This is also called as minus times reaction B. So say the shear force at the end point is minus times WL by 3. WL by 3 is more than WL by 6. We can write WL by 3. Now we want to say what is the variation. We know that variation is parabolic. So what is the slope here? Since the loading intensity here is 0, we can write that slope. We know that dV by dx equals to loading intensity. Loading intensity is 0. That means your shear force would be a straight line. So your shear force slope would be now we say that if the loading intensity here is 0, that means that slope of the shear force diagram is 0. So your shear force diagram slope is 0. Then what is the slope here at support B? We have that we know that the intensity here is W. That means there is some slope of W. Let's say this is your slope W, but it is we can write slope is negative minus W, because load is downwards. We have that dV by dx equals to W when loading was upwards, but here loading is downwards, minus W. So we got some slope here. We need to connect the two. Let's say this is your curve. Let it cuts the reference line at X from your support A. We need to calculate that value of X. So we have that if there are n number of critical points in SFD, and if the SFD is also changing its sign I times, then the bending moment diagram has that n plus I critical points. So for your bending moment diagram, one more critical point has been created. That's this one. And initially there were 2 critical points for bending moment diagram. Firstly, we want to say what is the value of x. Then we can calculate the moment at x. Say the shear force at x. We know that shear force at this x becomes 0. We calculate that WL by 6 minus WX squared by 2L. Then we can calculate the value of x. That comes out to be equals to say that L by root 3. L by root 3, is it so? L by root 3. Yeah, L by root 3. So your x becomes L by root 3. Now we want to calculate the moment at x. Say summation of moments at x equals to 0. So we can write WL by 6 acting in clockwise direction, WL by 6 into x, and that area of that triangle is half of W was your W by L into x, and it was acting for x at say x by 3 from your section x, and then moment x acting anti-clockwise direction equals to 0. So your moment x becomes WL by 6 x minus WX cube by 6L. Yeah. So your variation of that bending moment is a cubic variation. So moment at 0 becomes 0. Moment at L becomes say that this is also becomes 0 when you substitute the value of x equals L, and we want to calculate the moment at shear force becomes 0. That we calculate the value of x comes out to be L by root 3. We want to calculate the moment at L by 3. That equals to WL by 6 into L by root 3 minus WL by root 3 whole cube by 6L. Then we calculate that moment at, we can also write that moment maximum. That comes out to be equals to WL square by 9 root 3. This is standard result, WL square by 9 root 3. So your bending moment at x becomes that WL square by 9 root 3. That's positive value. So we have that cubic variation, 3-degree curve. This was your 2-degree curve, parabolic variation. This is your 3-degree cubic variation. So once you solve the SFD and BMD, try don't forget to write that this variation is 3-degree, this variation is 2-degree, this is cubic, this is parabolic. That makes that differentiable, that if you have two curves, SFD and BMD, both are like curves, then you differentiate that it is 2-degree, then and this is your 3-degree curve. So we know that dm by dx equals to v. Here the slope of the bending moment diagram would be equals to shear force, positive shear force. That means your slope is your WL by 6, and your variation should be such that then if the shear force is 0, that means slope of the bending moment diagram is 0. So your slope of the bending moment diagram here is 0. Then you need to connect the two by a cubic variation. Here there is also that same. The slope here, it has to be equals to minus WL by 3. Slope, this slope is more, but it is negative value. Okay. We forgot that to verify that we know in the previous question we said that the concept of that symmetric beams are symmetric loadings. We said that if your loading was symmetric, as we have that symmetric loading, once the loading was symmetric, the reactions that's reactions, BMD, and deflected shape is also symmetric. If you want to make the deflected shape of this curve, the deflected shape would be this way. It is symmetric about, say, this is your reference middle part, mid span. About that, the deflected shape is symmetric. Now, if you want to say what are the values of reactions, we got the real value of reaction here, WL by 2. Here also reaction of WL by 2. So it's symmetric. Then we got the bending moment value, bending moment diagram of that WL square by 8. So this is also symmetric about the mid part. But the shear force diagram is, it's not say a mirror image. It's one is upwards, next one is your downwards. Let's have one more symmetric problem that say this one, a simply supported beam subjected to loading, that maximum loading at mid, say this is your L by 2, this is your L by 2, and it varies linearly. So your uniformly varying load with a maximum intensity of W at L by 2 and 0 at the ends, say support A and support B. Let's have that, let's say the reaction here is reaction A and reaction B. We can write A plus B equals to, we can directly also say that, now we are mature enough that we can say the loading is symmetric. We can have that this part of the loading would become would be taken by the support aid, so the reaction here will become that WL by 2, that area of that triangle 1 by 2 W into L by 2, that WL by 4. Or we can say that area of that triangle A plus B equals 1 by 2 area of the triangle, that W into total length is WL. So then we say summation of moments at say moment at B equals to 0. We can write, let's say the centroid of this part acts here and centroid of this part acts here. We can say A into your length L clockwise moment about point B, and then the effect of this part, say AL, it's acting in the anti-clockwise direction. Say area of that triangle is W, half of that W into L by 2. This acts for a distance of, say this one is your 1 by 3rd of L by 2 plus this length is your L by 2. Then the effect of this this triangle, that is that's also the 1 by 2 W L by 2 acting at a distance of 2 by 3rd of L by 2, then equals to 0. Then you can calculate the value of reaction that will be equals to WL by 4. Similarly, that is also reaction B. Now since we say that we can directly say that the beam is symmetric, loading is symmetric, your shear force diagram is not symmetric. That means one part has to be upwards and one part has to be downwards. Once we got the shear force upwards equals to WL by 4, then the variation, say that the slope here is 0 because the loading here is 0 and the loading here is maximum. We can say that here the shear force has to be 0, then we connected that since it's a 1 degree curve, it has to be 2 degree curve. Then we have to connect to the 2 points, critical points. Here the slope equals to W. Slope is here value of W minus W because the loading is downwards. Then same curve has to be followed downwards. Say slope here is 0. The value of shear force at point B is also WL by 4, but minus times WL by 4. If you want to make that bending moment diagram, you can say that one more critical point for bending moment diagram is your at L by 2. You can write that. You can say you can calculate the value of bending moment diagram, value of bending moment. So for that, let's take that section now. So let's say we want to calculate the value of we know that we got the value of reaction A equals to WL by 4. Now you got the section in the region A, C. Let's say the mid part is your region C, in the region C. But before C, say C was here somewhere. We got the section before C. Let's say the shear force here is Vx, shear for bending moment Mx, and we have the loading that uniformly varying load. The loading here is W by L into X. We can say what is the shear force variation. We can write WL by 4 and minus area of the triangle 1 by 2 X into WL by X, W by L into X. Then you have the shear force minus Vx equals to 0. We can write as Vx. Then the value of, say, value at X equals to shear force at X equals to 0 equals to WL by 4, that we already plotted. WL by 4, and the shear force at X equals to L by 2 at the mid. We say that WL by 4 minus 1 by 2 L by 2 WL L by 2, that's WL by I think WL by 4 inverse minus 8 inverse. Yeah. The mistake here is that the that the loading intensity is varying from W to 0 in the length L, not in the length total L. It's varying in the length L by 2. So we forgot that it's varying by in the region L by 2. If you write it here W L by 2, it would shift upwards. We can say the overall value becomes that WL by 4 minus WL by 4, that's the value of shear force equals to 0 at the mid. Similarly, for the next part, for the part CB, we want to cut section C. We want to cut section at X. Let's take the section X. Let's make the problems more difficult and such that you can grab all your shear force and bending moment diagram. Let's cut a section at section X from A. We want to check the value of shear force. Say your shear force diagram is like that, loading diagram is like this, and say here the value of shear force is something. Let's say the shear force here is some value of W dash. Here we know that the loading here is W. Say the shear force here is Vx, moment bending moment Mx. The reaction here was WL by 4. We have that this length equals to L by 2, and this length equals to value of X. Centroid here and centroid. Oh, it becomes very difficult. Like, we don't have to go for the real crazy part. This might become very difficult. The next case was that if you cut a section from here, then you since the beam was symmetric, there was no need to cut this section. If you cut this section, it would take more time to solve. Then we need to do now, say summation Fy goes to 0. Then we write WL by 2 plus minus area of that this triangle W 1 by 2 W per L by 2, and then downwards this weight, this area of that trapezium. Say the value of here W dash has to be say in the for the length L by 2, we have that W, but for the say this one is your X minus L by 2, and this one is your L minus X. Then we can get the value of W dash. By similar triangles. Then it becomes a function of X, so it becomes very calculation. That the calculation becomes very much. So we can avoid that and skip to the good part. Okay, we got the shear force. We got the shear force up to this point. Similarly, the shear force, we can, for this part we can calculate the shear force in an easy way. That let's take that section in this way. We know the reaction here, the WL/4. The reaction B is WL/4, and we cut the section here at x from A such that x is less than L/2. Similar to that, what we solved for A, and you can get the value similar to what we got for A, but in the downward direction. So once you got that, we can calculate for the bending moment. We can calculate the bending moment values. Say that we have the equation for why is the section we have got already, this one. Let's calculate the moment mx, bending moment mx. We write summation mx goes to 0, that WL/4 about this point, say WL/4 into x, and say the centroid is here, and the area of that triangle 1/2 W/L/2 into x into your length x. This is your area of that triangle. It acts at x/3 from A. At that, it acts at x/3 from your section x, and your moment mx is negative, so we can write it as mx. So your moment at 0 at x equals to 0. So your moment at x equals to 0 is your 0. Moment at x equals to L/2 is your WL/4 into L/2 minus 1/2 W/L, and this was your 2, it goes upwards, 2/2 W/L. Your x square, your x cube becomes L cube by 8 and 1/3. Once you calculate that, you say that 8 inverse minus 24 inverse, you can get WL square by 12. WL square by 12. So this is your next result, that moment at the midspan, equals to WL square by 8. WL square by 8. Since the shear force here is 0, then the slope here has to be 0. So your value of bending moment diagram is WL square by 12. Here the shear force is not 0, so your slope is not 0. Here the slope is not 0. Slope equals to minus that shear force at B. Now we don't write that every time. Say the diagram would look like this one, a cubic variation, that 3-degree curve, positive value, bending moment diagram. So since the beam was symmetric, since the loading was symmetric, your shear force diagram is not symmetric, but your reactions are symmetric. And your bending moment diagram is also symmetric. And if the deflected shape is to be plotted, it will be let's say some sort of this way. It's also symmetric. We have one more question on that symmetric problem. That say you have let's say problem. Say you have a length of L equals to 10 meter. Your simply supported beam at 5 meter and 5 meter, and the loading is now such that at the supports it's maximum and at the ends it's your 0. At the ends we have that 5 kilonewton per meter. W equals to 5 kilonewton per meter. Here also 5 kilonewton per meter. we need to get the shear force diagram and bending moment diagram. So it's also a symmetric loading. We have that symmetric loading. We can get the BMD reactions and deflected shape symmetric. If you calculate the reactions, now this question is similar to the previous question, so we can say that centroid here and centroid here, we can get the reaction A and reaction B equals to W into that length L by 2 area of that triangle. That comes out to be equals to 12.5 kilonewton, and this is also 12.5 kilonewton. If you want to say what is the shear force diagram, say this is your reference line. We have that shear force at the ends equals to 12.5, and at this point, since the reaction is at the support B, reaction is upwards, that means it would have been just before the support B, shear force would have been minus 12.5. Then the support B is upwards, reaction upwards, such that overall shear force at the ends comes out to be that that then the final value, it's like balanced, so that if it is WL by 2, it has to be, if it is 12.5 positive, it would be negative 12.5 shear force diagram. Or we can calculate it by cutting the section. Let's cut the section at say let's cut the section at x such that the intensity here is W dash and intensity here is 5 kilonewton per meter. Say the centroid acting for the UDL here, and for the triangular view UVL, we have the centroid here, and the reaction here is RA equals to 12.5, and say that the shear force at x equals to Vx and moment Mx. We have that value of x. This is valid for the span AC, for span AC. If x is in a, say, value of x is greater than 0 and less than or equal to value of 5 meter. Now we need to calculate, say that summation Fy goes to 0, we can write 12.5 kilonewton, and your UDL of that, we need to get the value of W dash first say that W dash, no, there would have been one more triangle if we connect it up to the point C. Say here that UDL is W dash, that variation is W dash, here it is 0, and this distance is your 5 minus x. We say that W dash for 5 minus x by similar triangles, that W dash by 5 minus x, that is equals to 5 kilonewton per meter. That's for per 5 meter length. So if we calculate that, what is the value of W dash? That comes over to be 5 minus x. So it's easy. Say that 5 kilonewton per meter is varying in 5 kilonewton per meter. This 5 kilonewton per meter is varying in the 5 meter. So per 1 meter there would be a change of that 1 kilonewton. Yeah, there would be a change of 1 kilonewton. So if you say that what would be the value, what should be the value after you go from say x to x, we say that maximum it was that 5, and how much x it has rated, that you have to subtract. Say the equation becomes y equals to that c minus mx. Your slope becomes tan 45, tan theta. Tan theta is your perpendicular by base, say that 5 kilonewton per meter by 5 meter, that is your 5, that 1 kilonewton is your tan theta. So your slope, that's your slope m, and your c is your maximum intercept, that is, we can say that 5 minus x, that's your y equals to 5 minus x. So finally we got the value of w dash, that comes out to be equals to 5 minus x. 5 minus x. Let's write the shear force equation. We can say that 12.5 summation Fy goes to 0, 12.5 upwards, and your UDL of W dash, your W dash becomes minus times 5 minus x for distance of x, and your UDL, your uniformly varying load, triangle minus 1 by 2 5. The difference here is 5 minus of 5 minus x, so your value becomes equals to x. We can write the value of triangle here is x value. So area of the triangle becomes x into x, that's your x square. That then the shear force downwards minus vx equals to 0, so your shear force at x becomes equals 12.5 minus that minus 5x plus x square minus x squared by 2. After substituting the values of shear force, that x equals to 0, we can get the value of shear force equals to 12.5, that we have already plotted here, that 12.5 kilonewton, and the shear force at x equals to 5 meter, and we can get the value by substituting the value at value of 5, that x equals to 5, we can get 12.5 minus that 5 into 5 minus, this was your x square, this one was your x square, so we can write as 5 into 5, that minus 25 by 2, that comes out to be minus 50. Minus 50. Minus 5 into 5. 5 into 5 is your 25 minus x square. Yeah, it's your plus x square minus x square by 2. That comes out to be equals to 0. When you substitute the value of x equals to 5, you get the value of shear force equals to 0. So your shear force at the midspan, that equals to 0. Now you have to connect the two by a line that is a function of x square. It's a function of x square, so your variation is parabolic. So your variation is parabolic. The slope here has to be the slope of 5 kilonewton per meter. So your slope is there, some slope is there, so we had to make it equals to 0. But we need to keep the slope at supports at the point C equals to 0. So we need to make it again. Here the slope has to be 0. Say the slope has to be 0 here. Then we join the two by a 2-degree curve, parabolic variation. And for this part, if you solve this way, that if you cut the section from support B, you would get the value similar to what we got in this region. Then since the loading is symmetric, we can get the values similar to what we got in this region. you can say, let's have this one. So the slope here is theta tan theta. Slope equals to, you can write as the value of UDL intensity, that is your -5. Okay. Now we need to get the bending moment diagram. Bending moment. For that we need to get the bending moment equation. So we got that. We say, let's say summation of moments about x equals to 0. So we write 12.5 for a distance of x, and we have that rectangular portion, that UDL, with the intensity of 5 minus x. So we write -5 minus x. This acts for a length of x and acts at a distance of x by 2 from your section x. Then your triangular variation, that half of base is your x, and your peak is also x. This is your load acting at a distance of say acting at a distance of that this one 2 by third of x, and your moment is also anti-clockwise direction. We can write as that bending moment at x. Though when we calculate the value of moment at x, do we have the equation? No, we don't have the equation. Let's write the equation. We can write 12.5 x minus 5 x squared by 2 minus plus x cubed by 2 minus your x cubed by 3. So your maximum variation, maximum value of maximum degree is your 3. So your bending moment diagram would be a cubic variation. So when we substitute the value of moment at x equals to 0, then we have the value of moment equals to 0, bending moment equals to 0. Then we say, what is the value of bending moment at x equals to, where the shear force changes sign, that's at x equals to L by 2. Your L by 2 is your 5 meter. Then you solve that, substituting the value of x equals to 5 meter, you can calculate the value of bending moment into 5 minus 2.5 into 25 plus 125 by 2 minus 125 by 3. That we got the value of 20.833 kilonewton meter. So we have that dm by dx equals to v at v equals to 0. We have that moment is maximum with respect to their neighbors, with respect to its neighbors. It means where the v is 0. So we got that moment at end is equals to 0, since it was a simply supported beam, and the moment at the midspan we got the value of 20.833. Also we know that if shear force is 0, then the slope of the bending moment diagram is 0. So here the slope is 0. Then we need to connect the two by a 3-degree curve. Write it as 3-degree curve. This is your positive bending moment, and the slope here is a slope of 12.5. We can write as slope equals to 12.5. Then we have that. Then we join the two. Similarly, we have that this side also. So your maximum bending moment is this one, and maximum shear force this one. Let's frame the question now. Let's make it more interesting. So we got the maximum. We got the maximum shear force equals to your 12.5 kilonewton, and your maximum bending moment equals to 20.8333 kilonewton meter. And the span of the beam was 10 meter, and the intensity was that varying. Now let's make one question that you need to design a beam in which there is only UDL. For UDL, W such that Vmax equals to 12.5 kilonewton and moment max equals to 20.8333 kilonewton meter. So when we say design something, we say that its dimensions. Designing means dimensioning a particular section. So let's say that the question says, let's say you have a length L. See, your shear force and bending moment is not a function of your width and your depth of the member, but it is a function of length. So if we say that the length is L and there's only a UDL acting, so we want to get the equivalent bending moment. Say that W is your equivalent, that intensity of the loading. So we can write the equation that we already know the results, that the shear force diagram looks like this one. At the mid, shear force is 0. At the ends, your shear force becomes WL by 2, negative, positive, and the bending moment diagram looks like this one. That if it is the middle part, then we have that here the shear force is having some slope of WL by 2, and the slope here is 0. Then we connected the 2. We have that result that bending moment here is WL square by 8 positive. If you substitute the value that WL by 2 is your maximum shear force, and that we equate to what we got, that 12.5 kilonewton, and your WL square by 8, that equals to 20.833. Then we substitute the value of WL by 2 in this part. I say that WL by 2 into L by 4 equals 20.833. Then we write 12.5 L by 4 equals to your 20.833. Then we get the length of beam equals to 6.66 meter, and the UDL intensity is your 3.75 kilonewton per meter. So next one is your next question. Let's have next question. Draw the shear force and bending moment. Draw the shear force diagram and the bending moment diagram. Next question, that draw the shear force diagram and bending moment diagram for your question is that you have a simply support beam, supports at A and D, and the total length is 20 meter. At 10 meter from A, you got a point load of 600 kilonewton, and after that, at 5 meters, you got a concentrated moment of 4000 kilonewton meter, and this is also your 5 meter. So for that, we can get the reactions. Firstly, we can solve the reactions. Say summation Fy goes 0, A plus B, A plus D, that equals to 600. Since the vertical force is only 600, the moment is not included in the forces, so we can say A plus D equals to 600. Now we can say summation of moments at, let's say moments at D equals to 0, which implies that A into 20 clockwise moment about D and minus 600 anti-clockwise at a distance of 10, and a clockwise moment of 4000 kilonewton meter equals to 0. So we get the value of A equals to 100, A equals to 100 kilonewton, and B equals to 500. Is it 500? Yeah, 500 kilonewton. Now we have to make the shear force diagram and bending moment diagram. If we want to make it directly, we can say say the shear force we got at A, that's equals to reaction at A, the value is 100. Then since in the span A, that first to 10 meter, there's no external load, we can say there's no external load. We can write in the side that for let's say the here is it is B, here it is C. We write for AB dV by dx equals to 0, because loading is not there. That means your V is remains constant. So we can connect to the we can go straight horizontal. You can go horizontal up to the point just before your point B. Then we say that for the point load we have that dV equals to minus P, that change in shear force. That we can say that V shear force just after B, that equals to shear force before was your that was your shear force before was your 100, that minus P is your 600. So you got the minus 500. Minus 500. Now in the span BC also there is no external force, there's no external loading. We can write we can keep the horizon, we can keep the shear force diagram horizontal, and because of the concentrated moment, there is no effect in the shear force diagram at that point where concentrated moment occurs. We can write the statement also, and after that it also continues till point D. This was your reaction D. Then after that, since it's negative, then after that your reaction of 500, we can also write that dV equals minus P. We need to get the shear force at point D, that equals to shear force just before D was your minus 500, that P2 minus P1 equals to minus P. We can write VD minus P1 was your just before D was your minus 500 equals to minus P. P was your value of P was your value of reaction D. P is your value of reaction D. So your reaction D is your 500. So we can write VD equals to 0. So your that final shear does make any sense? No, it doesn't make any sense. That it is not making any sense. That say say at D there is a support. It's giving a reaction of 500. If cut just before D, we say the shear force here is Vx. We can get that shear force at x equals to 500 minus times. That means shear force is 500 negative. So your shear force here is minus 500 negative. That's also, that means the shear force here is also minus 500. Then we join the 2 points because of the reaction that the reaction D offers. It becomes then finally reaching the point, that reference line. So we can write the one we can write one statement that concentrated moment that you applied, that 4000 kilonewton, does not affect the shear force diagram, does not affect the shear force diagram, but it only affects the support reactions. But we can say that once the support reactions are changed, your shear force diagram is also changing. But so to make the statement more clear, the concentrated moment does not affect the shear force diagram. We can write it at the point where the concentrated moment acts, M external acts, where we are concerned about the point itself, that this point, about this point. Because of that effect, because of the moment, there is no change in the shear force diagram. But we got the reaction that because of this, we got the reaction that 100 here, and because of that, the reaction shear force diagram looks like this. If there was no external moment applied, so the 600 kilonewton was at mid span, so the reaction would have been that at this support it would have been 300, and the shear force diagram would have been this one, 300 and 300 for 10 meter and for 10 meter. Now we need to get that bending moment diagram. Let's say this one, this is your reference line. We know that when we derive the equations, we got that dm by dx equals to v, or in other words we can write that m2 minus m1 equals to area of SFD between the 2 points. We know that the moment at the end point is 0, which implies moment 1 is 0, so we can get the moment 2, that at 10 meters, moment 2, that means moment at 2 equals area of the shear force diagram up to that point. That means this is your 10 meter and this is your 100 kilonewton shear force, so we can get the value of moment 2 equals to 100 into 10, that's your 1000 kilonewton 1000 kilonewton meter BMD. And the variation is, if it is horizontal, it has to be a linear variation, 1 degree. And then after that, once we got the value of shear moment at this point, now if we calculate the moment, since in this span there's no change in shear force diagram, and we also know that, so but external moment is acting there at point C. So up to that point C, we want to say what is the moment value up to the point C. So we want to calculate the moment at C. We can use the same equation, that moment C minus moment at what we call as moment at B equals to area of the shear force diagram between the 2 points. The area of the shear force diagram between the 2 points is your negative 500 into the length 5 meter. So your moment C equals to moment B was your 1000 minus 500, that's your minus 2500. That comes out to be minus 1500. Is it so? Minus 1500, yeah. Once you got the value of shear force, that bending moment equals to minus 1500, we can say that if it is your 1000, then you have that line, say this one is your minus 1500. Why straight? Because your shear force diagram is horizontal. That means your bending moment diagram would be a linear variation. So your value at moment at C comes out to be 1500 negative. So this one is your negative, this one is your positive. So it cuts the span at some section. We would be calculating it. So then after that we can write the final value of moment D. We can say moment D equals to moment at C plus area of the SFD between the 2 points. This area comes out to be equals to that rectangle 500, that 500 into 500 into your length of 5 meter. That means uh, is it 5 meters? Oh, we forgot that we had a concentrated moment of 4000 kilonewton meter acting at your span at your point C. We also know that when we derived the equation for the effect of concentrated moment, we derived the equation for your concentrated moment m external between the span at a section dx tending to 0. We write that, say the moment here is m, here the moment is m plus dm. Then we derived that here the shear force is v, here the shear force is v plus dv. Then we derived that uh, change in moment between the 2 points, that equals to uh, say if the dx is tending to 0. That is the case for concentrated moment, because concentrated moment acts at a point. Then the dm equals to m external. M external positive if the when we derived we got the value as positive m external. If the m external is negative, we can get is minus m external. So we can write as m2 minus m1 equals to m external. So same equation we can write here. Since your m external is 4000 clockwise, that means this is according to this equation. That means your m external is positive. We can write that m2 minus m1 equals m external. We can write that. Let's write that we have that at point C. Let's write in the side. We have that at point C. At point C, we have that uh, moment. We need to get the moment just after, because we are moving from left to right. So we need to get the moment that is moment just after point C. That equals to moment just before C. That was equals to moment C that we calculated as 500, 1500. Let's keep the sign also. We say that moment just after C equals to minus times now moment 2 minus moment 1, moment 2 minus moment 1 equals to moment external. Moment 2 is your moment just after. We want to calculate just after your point C. What is the moment that moment C. Say moment just after C is your moment just after C minus moment 1. What's the moment 1? That's minus 1500. So we can write minus of minus 1500. That equals to your moment external. Your moment external you are applied as clockwise 4000. So we can write moment just after C is your 2500 kilonewton positive. So your 2500 kilonewton, say 2500 kilonewton is here. So this is your 2500 kilonewton, and there is just, we can say it rises by an amount of m external. So your BMD rises by moment equals to m external if the m external is acting clockwise direction. So let's say the support say the reaction say the moment was at this point equals to this one, then it will rise by an amount of m. So initially it was minus 1500, then it rises to by an amount of 4000. So your net value becomes positive 2500. Now you join the 2 points by a straight line, and after that we can get the value of moment at D equals to moment at C. This moment at C is the value that moment just after C. Okay, right at moment just after C plus 5000 plus that the value of that UDL was minus 5000 into minus 500 into that shear force diagram, area of the shear. This was your area of the shear force diagram between the 2 points. So this one, the shear force diagram area is your 500 and your length was 5 meter. So your that moment D equals to moment, we have that equation that moment 2 minus moment 1 equals to area of that SFD. That moment 2, that we have moment D equals to moment just after C, that was 2500 and minus 2500. So your moment comes out to be 0. So that's true because your support is simply support. So joining the two by a straight line. So this is your bending moment diagram. So now we need to get the value that what's the value of this x, why the bending moment changes the sign. So we can get the value of, we can get it by the symmetric triangles. uh, before this question we were solving questions uh, mm, generally by that method we called as analytic approach, that cutting the section and getting the equation of moment mx and that shear force vx. Then where out the section cuts, we say that the shear force was there 0, then we equate, then we get the value of x. Now in this method, this one is your smart method. We do here just similar triangles to get the value of that x where it cuts. So we can get it using the concept of similar triangle. We can say that the slope is this triangle. We had the true triangles. One triangle is this one, next one this one. What is the length of this part? We have this part C to B to C is your 5 meter. B to C is your 5 meter. So this one is your 5 minus x. So we can write as that 1000, that value of bending moment is 1000. It has become 0 in length x, and similarly 1500. We don't have to write the sign here. We are focusing on the magnitude, that this triangle, say this is a triangle of 1500 for length of x, 5 minus x. We see that 1500 has been becomes 1500 becomes 0 in your length 5 minus x. So after calculating, you can get the value that, let's say this is your 5000 5000x 5000x minus 1000x equals 1500x. So your x value becomes, is it 2 meter? Yeah. So your, if it is 2, it has to be 3 meter. Okay. So let's have, should we go for one more problem? Let's have one more problem. Say let's say you have a cantilever beam and the uniformly varying load acts such that its maximum intensity is at the free end. and 0 at the fixed end. So your length is L. Get the shear force diagram and bending moment diagram, and solving by analytic method. So let's cut the section. We don't have to get the reactions. We can cut the reaction, or let's get the reactions. It's up to us what we want. Let's say the reaction here is, we can directly solve the reaction, that is, after doing that summation Fy goes to 0. Then you can do now. You can do that now. So this reaction becomes WL by 2, area of that triangle, and the moment here, it would become say the centroid is acting here. We can say the total load of WL by 2 is acting at a distance of 2L by 3 from your support A. So your bending moment at A equals to WL square by 3. Then you make the shear force diagram. Here the shear force value is WL by 2, and the slope here is 0 because loading intensity is 0. Then here the slope is some value that minus W, so your slope is minus W. Then you join the two by, since the loading is 1 degree, you have the curve as 2 degree, shear force 2 degree. And for the bending moment diagram, you can say your bending moment is your minus WL square by 3. At this point, the next critical point is your free end. We know that at the free end there is no moment, so we need to join the two. The slope here, it has to be equals to WL by 2. So here the slope has to be WL by 2, positive WL by 2, and the slope here, it has to be 0 because the shear force here is 0. Then you join the two. So this is your 3 degree curve minus times WL square by 3. Taking the same problem, but changing the loading direction. So here it is W, length L, fixed support. Say the reaction here is also that WL by 2, and we can make that shear force diagram. Let's say you got the reaction as WL by 2 and you have a loading intensity of W, so we can make the shear force diagram that here it is WL by 2 and the shear force here is 0, and you can say WL by 2 minus area of that triangle WL by 2, that is 0 at the end. Now the variation has to be, it is 1 degree, it has to be 2 degree, and the slope here, it has to be value of W. So here the slope is W and the slope here is 0. So we need to join the two values, 2 points, critical points. The slope is positive, the value of shear force is positive, and the slope here is negative because minus W acting downwards. And for the bending moment, we can say that the bending moment developed here would be area of the triangle WL by 2, and the centroid is acting at L by 3 from your support A. So your bending moment at A becomes that anti-clockwise. That means your minus times, since the sign convention is that from the left, if the moment is acting anti-clockwise, you have hogging moment. So your bending moment diagram, that bending moment value is negative. So minus W L square by 6, and the bending moment here would be 0. It's your free end. At the free end there is no moment developed, bending moment. So we need to join the two values. So this was your 2 degree curve parabolic variation. So this PMD would be 3 degree cubic variation, I would say. Let's say that the slope here, it has to be slope equals to shear force at that point. The shear force at that point is your WL by 2. So your shear force that bending moment diagram would be a positive WL/2 slope tan theta, and the slope here it is 0 because the shear force here is 0. Then you join the two by 3 degree curve, and this is your BMD. So if you want to check the difference between the two, oh, see the difference? I made a mistake there in the first question. See, for the shear force diagram is okay. At the ends, your loading is maximum, so your slope is there. But here, slope is not. There won't be in slope in the SFD because your the loading intensity is 0. And similarly, for this part at the free fixed end, there is no loading, so your slope is 0. But for the end part, there is slope because your loading is there. And for the bending moment diagram, you are having a slope. You are having a slope that's equals to WL/2, WL/2. But here the shear force that the slope is 0. Yeah, it's correct. Now coming back to this part, see the shear force here is WL/2. That means there has to be a slope of WL/2 here positive, and the shear force here is 0. So okay, everything is okay. I thought there's some mistake. Okay, we have one more problem now. Say this one, 4 meter, 6 meter. Say you have, let's shift it downwards. Say you have a bar, or we can say plates. You have plates added. Say this plate is a 3 meter length plate, and after that you have one more bar or plate of 2 meter. Then you have applied a force of 2 kilonewton. Say this is your 2 kilonewton force acting such that this bar is 2 meter and this bar is 3 meter. Then we need to get the shear force diagram and bending moment diagram of your beam AB. Say this is your point C. So for this case, we had to do, we had to check the effect of this that these bracket plates or these bars, external bars, and the effect of that loading, how it's transferred at point C. So if we do free body diagram, if we make free body diagrams of these the external bars, we say, let's say this was your force 2 kilonewton meter, 2 kilonewton, and after that you have 2 meter. We want to say let the shear force here is V, and the moment here is moment M. We can get the values of moment and shear. We say that V plus minus 2 equals 0. That means shear force it is 0. It is 2. If the shear force wait okay, if we got the value of 2, the moment, we can say moment at this point, that clockwise moment of M and clockwise moment of that 2 into 2, that's your 4, equals 0. That means moment is minus 4. That means it is in anti-clockwise direction. So if it is in anti-clockwise direction, that means that it should be of this way. The shear force was this one. You can keep it as double arrow, that as a full arrow. We can keep that value of 2, and the bending moment here it is anti-clockwise 4 kilonewton meter. Now the same, these are the internal forces at this joint, at this section or joint. At this section, if on one side the section, we know that the shear force is the summation of forces on either side of section. If you calculate from this side, you will get same shear force, and if you calculate from this side, you get the same value of shear force. So we say that the same values are transferred in the bar in this bar, say ZC. In the ZC, for the ZC we have that the loading here was upwards, that means the loading here would be downwards too, and the moment here was anti-clockwise 4, here the moment it has to be, yeah, clockwise 4. Then after that we have that then after that this is your bar. Now we want to check what is the value of these forces here. Then after that, let's say, since it's acting downwards 2 kilonewton, so your reaction here would be, say, 2 kilonewton. And the moment you are applying in the clockwise direction, it tries to rotate the bar this way, so the bar will uh, react this way. So that, no, it's wrong. Since the bar is going that way, we need to prevent the rotation. For that, we have to apply moment in the opposite direction. That moment in this direction. If you say what is the value of moment, say, let's say I assume that the moment here is anti-clockwise m. Say the moment at, say that this is your point C. We can say moment at C, summation of moments at C equals 0. We can say that clockwise 4 plus your anti-clockwise m equals to 0. That means the m bending moment at your C equals to your 4. That means assumed direction is correct. So we can remove this part, and we can make it smaller. So your moment here is m equals to 4. Now after the two bars are over, now we have the main beam of 4 meter, 6 meter. Okay, this was your beam, this was A, this was your B, 4 meter and 6 meter. Say if the loading here is upwards 2, at this point there would be a reaction of downwards 2. And if the moment here is acting in the anti-clockwise direction, here the moment it has to be a clockwise direction of 4 kilonewton meter. So finally we have transferred the loads on the beam. So now what we can do, what is the value of that reaction? The reaction is 2. So we can get the values of shear force and bending moment diagram. Let's minimize that shear force and bending moment diagram. We can say, firstly we can solve the reactions. We can say A plus B equals to total transverse force, that's your 2 downwards. Say this is your A upwards and this is your B upwards. Then we say summation of moments at, let's take at B equals to 0, which implies that A into 10 clockwise about 0.0, and your clockwise moment of 4 and your anti-clockwise moment of 2 into 6 equals to 0. That means A equals to 0.8. Is it 0.8? Yeah, it's 0.8. That minus 12 minus 4, that's 8 by 10, 0.8. So your reaction is 0.8 upwards. So your reaction A is your 0.8 kilonewton upwards, and your reaction B, it would be 2 minus 0.8, that's your 1.2 kilonewton upwards. Now we had to plot the shear force and bending moment diagram. So let's say this is your reference line. Here we got the shear force value equals to 0.8. We got the shear force value equals to 0.8, then there is no change, there is no loading intensity up to the point C. So we have a constant shear force diagram of 0.8 kilonewton. Then we have a point load of downwards, point load 2 kilonewton downwards, and there is no effect of concentrated moment at that point in the shear force diagram. Only the effect of concentrated moment would be there, that dp that dv equals minus p, dv equals minus p. So your your shear force v2 would be equals to shear force v1 was your zero point 0.8 minus of your p is your 2. So finally it would be minus 1.2 minus, then we have constant value because no loading is there, and finally it will become 0 because 1.2 minus of reaction B. This is your final SFD. And the BMD, for the BMD would say at the point, we know that at the point where shear force changes sign, uh, uh, let's make the diagram firstly, we can calculate later. Let's say it's your this is your bending moment reference line, diagram line. Yeah, see, we know that m2 minus m1 equals to area of SFD. area of the SFD is your between the two constant points, that moment at C. We know that moment at A equals to 0 because support is simple. It's hinged support, that moment is 0 here, and we want to calculate moment at 4 meter. That is moment at C. We know that moment at C would be equals to moment at 1, that is 0, plus SFD area is your that 0.8 into 4 meter. 0.8 into 4 meter, that is 3.2 kilonewton meter. 3.2 kilonewton meter. This is your BMD. So the variation is that if shear force is constant, that horizontal, that means x power 0, function of x power 0, that means your BMD would be x power 1 function. That's linear. So connected the 2 critical points by a straight line. Yeah, the point I was saying that once for the shear force diagram, there are n number of critical points, and if the shear force is changing sign I times, then the BMD would be having n plus I critical points. So we got one more critical point for shear force, that bending moment diagram at say at this point where shear force changes sign. Then we can also say that we want to calculate the moment. Now see there is external moment also acting. We know that m change in moment equals to m external if m external is acting only. Say m external for dx tends to 0. We got that m2, so we can say m just after, we can write that m just after point C equals to moment just before was 3.2 and plus your moment your m external. Your m external is clockwise moment. So if the moment is clockwise, then that means it is to be added. So your final value becomes 7.2 kilonewton meter. So your BMD jumps up by a unit of 4. The final value becomes 7.2. Then after that, let's say the moment here is mb, that's equals to moment 2. We know that moment 2 equals moment 1 plus area of SFD. That equals to moment 1 was your 7.2 kilonewton meter, and plus area of the SFD between the 2 points, that is this area. So we can write as minus 1.2 into length is 6. So we get the value 0. Then we connected the 2 by a straight line because your shear force is horizontal, so BMD is a linear 1 degree curve. So this is your BMD. Similarly, uh, if the bracket plate was installed opposite to the this direction, let's say the bracket plate was installed, say this was your beam, this was your beam, and 4 meter point C, and 6 meter point B. A length was this 3 meter, 3 meter, and let's say this plate or this bar has been uh, installed in the region CA. So this is a 2 meter, this is the 3 meter, and loading was 2. Similarly, we can have the moments now like this. There would be 2, this would be 2, this would be 2 2s are 4, and for the next one it would be, if it is clockwise 4, here it was anti-clockwise 4, and the reaction is transferred. If it is vertical upwards, then it has to be downwards 2, and for this it is clockwise, here it would be it is 4 in the clockwise direction. It is anti-clock, it is clockwise, it's 2 downwards, it was 2 upwards, and it has transferred. Now the reaction will be transferred, that the reaction here it is 2, and the moment here was clockwise, so here the moment it is anti-clockwise moment of 4. Then we can say, we can get the values of reactions, we can get the value of reactions. Now let's solve for the reactions. Say this was your 4 meter, this was your 6 meter, this is your 4 kilonewton meter, this is your 2 kilonewton. Say summation of moments at B equals to 0. We can write A into your 10 meter, then clockwise moment of, then anti-clockwise moment of 4 minus 2 into 6 equals to 0. That means A equals to 1.6 kilonewton. So in the shear force diagram we can write 1.6 kilonewton. Then there is constant line up to the point of point C, because no external UDL is acting, so your slope is constant. After that, no effect of concentrated moment in the SFD, but only the effect of that concentrated load would be there, that dV equals to minus P. So the shear force just after point C would be equals to shear force before was 1.6 minus your load is acting downwards, so your net value 0.4 downwards, minus 0.4. So it remains constant. Then finally it would be equals to 0.4 here. So if you calculate value of P, that can be calculated, that 2 minus 1.6, that's 0.4. So it is your SFD. And for the BMD, we can write that up to this point there is no moment. At support A there is no moment. We can write M2 equals M1 plus area SFD, area of the SFD. We can say for the moment 1, there at the support there is no moment, so moment 1 is your 0. That means 0 plus area of the SFD between the points AC, that is your 4 into your length 1.6, that's 6.4, a moment of 6.4. Say the moment here is 6.4, you join the 2 by straight line, that's your 6.4. Then after that we have that dm equals to m external. Your moment just after, we can say moment just after C is your moment just before was your 6.4 plus m external you are applying in the anti-clockwise direction. So if the moment is in anti-clockwise direction, that means that moment is your negative minus 6 minus 4. That means finally you get the value as that 2.4. So so your BMD drops by an amount of 4 kilonewton meter, such that the final value comes out to be 2.4. Then after that we need to get the value of moment at the end. Moment at the end equals to moment at 1 plus area of the SFD, we can write moment 1 is your 2.4 positive, and plus area of the SFT is your negative 0.4 into length 6, that means 0. So you need, so your moment is 0 because support is there, simple support. So you connected the two lines by 2 points by a straight line. This is your 1 degree, this is also 1 degree, and this is your 0 degree. Let's take one more problem. So this is your cantilever beam of length 1, 3, 4, 1 meter, 3 meter, and 1 meter. So your load UDL is acting for 3 meter with an intensity of 2 kilonewton per meter. Get the shear force diagram and bending moment diagram. Let's say we write that summation Fy goes to 0. Let's solve for the reaction. Say reaction here is A, horizontal 0, and the moment ma. We can write that summation Fy goes to 0, so we can write 2 3s are 6 downwards plus reaction A upwards equals to 0. That means reaction A is reaction A equals to 6. Then you make the shear force diagram, that here the shear force diagram, shear force equals to 6. Then there's no change in the shear force because in this region there's no UDL acting. After that there is no change in shear force. Then after that we write that dV by dx equals to loading intensity W, but the loading here is minus because negative loading is downwards. We write that V2 minus V1 equals to area of the loading diagram. Area of the loading diagram. So your shear force. So next critical. Once you got the one critical point, your next critical point is your point where the shear that UDL is UDL ends. So your next critical point is your point where the shear force at UDL ends. We want to calculate the shear force at that point. Say V equals V at 4 meter. We say that V at 4 meter equals to shear force at 1 meter was your 6 plus 6 plus and area of the loading diagram. That loading diagram is this one. Loading intensity of 2 kilonewton per meter for 3 meters. We can get the value of shear force equals to 2 kilonewton positive. No, this is acting downwards, so it's UDL is acting downwards, so your area becomes minus 2 kilonewton per meter into length 3 meter. So your value becomes 0 at this point. So from this point to this point, since loading was constant, a function of x power 0, so your SFD would become a function of x power 1. So your function of x power 1, that's linear variation, linear. And after that there's no shear force, since we got the shear force here 0, and in this part no load is acting. There's no shear force in this part. We can say, let's say this point is D. We want to calculate the shear force at D. We write that shear force at D equals to shear force at this point C plus that any UDL is if there is acting area of UDL. This is also 0, this is 0, that means VD is also 0. Now if you want to make the bending moment diagram, for that you need to calculate the moment at A. Let's say the moment at A, we can write summation of moments about A equals to 0. That means bending moment at A minus m times minus bending moment at A, and your reaction into 0, and your clockwise moment of 2 into 3. This becomes your load. It acts at the centroid, and from A it acts at your centroid was 1.5 meter plus 1 meter. So your moment at A equals 2.5 15, moment becomes 15 kilonewton meter. That means the direction assumed is correct. That's anti-clockwise direction. So if you want to make the BMD, try to make the BMD below the that shear force diagram, because it becomes it becomes easy to draw these diagrams once the loading is increased and that loadings are complex. So for that, try to make the BMD that below your SFD. See, we got the value of bending moment at A equals to minus 15, minus 15, minus 15 kilonewton meter, and we want to calculate the bending moment value at 1 meter from A. We can say moment at 1 meter from A equals to bending moment at A. That's your bending moment. We can write it in terms of this one. dm equals to area of SFD. So we can write that m2 minus m1 equals to area of the SFD equals to 6 into 1, 6 into 1 positive. So moment 2 equals to moment 1 was your minus 15, and after shifting it would remain minus 15 into plus 6, that's minus 9, minus 9. Say minus 9 is here, minus 9. Since the variation of the shear force is constant, horizontal, it's not function of x, so your BMD would be a linear part, 1 degree. After that, the area of the SFD, we can say what is the bending moment value at point C. What is the bending moment value at point C? We can write bending moment at point C equals to bending moment. We can say bending moment at C minus bending moment at 1. That 1 means that after 1 meter, we can say that is equal to moment 2. Keep the confusion away. We can write moment 2, and that equals to area of the SFD between the 2 points, that this point and this point. The area of that triangle is your 1 by 2, 6 into 3, 1 by 2, 6 into 3. That's positive. So your moment C becomes 9 plus moment 2. Moment 2 is your minus 9. So your bending moment at C comes out to be 0. So your bending moment at C comes out to be 0. And since the shear force at C is 0, that means the slope here is to be 0. And the shear force here is 6. That means here it has to be some shear force. There has to be some slope. Then after that, the variations for the shear force diagram is 1 degree linear. For the bending moment diagram, it has to be a parabolic variation, parabolic variation. So we join the 2 points. So this is your curve. Okay, this is your BMD. And after that, there's no lower and there's no shear force diagram. We can say there's bending moment diagram, a straight line. Let's take one more problem. Say say the you have say the you have a cantilever beam with a UDL intensity, say uniformly varying load of W at the cantilever end, and becomes 0 after length L. Then after that it continues for another L in the opposite manner with same UDL intensity W kilonewton per meter. We need to get the shear force diagram and bending moment diagram. Say this is your support A, and say the reactions developed here is RA and moment A, MA. The centroid of this triangle, uniformly varying triangle here, and the centroid for this one is here. We can say that summation Fy goes to 0. For that, we will write that reaction A upwards plus that area of the triangle downwards half of WL, and the area of the triangle acting upwards plus area of the triangle acting upwards, that WL equals to 0. That means your reaction A equals to 0. Now if you say summation M at summation of moments at A equals to 0, we can write, let's write that moment A would assume that minus MA anti-clock, and the effect of this triangle, this is clockwise, plus half of the loading intensity W into length L. It becomes your load. It acts at L by 3 from your support A. Then the for the next triangle, it acts as anti-clockwise direction with respect to your support A. So we can write minus area of the triangle is WL by 2. Now it acts at L plus 2L by 3. This is your L plus 2L by 3. So you can get the value of moment A equals to minus 2WL square by 3. Let's solve for the moment. That's 6 inverse minus 2 inverse into 1 plus 2 by 3. It's 2 by 3 of WL square minus 2 by 3 of WL square. So your moment is moment acts in the negative. So what does negative mean? That means that we have assumed actually anti-clock, but the moment actually developed is clockwise. So we can see it. So because of this triangle, since it's that distance why it acts is smaller, so the clockwise effect of this one is smaller. So let's say the moment developed was m1, but because of this triangle, same amount of load is there, but its length, its perpendicular length between upward the point A is more, since it tries to rotate it in anti-clock. So final moment net would be in clockwise direction. So now we want to make the SFD and BMD. Say this was your reference line for shear force diagram. Here the shear force we got equal to 0 because reaction A equals to 0. So reaction A equals to 0. Then after that, we can write what is the next critical point. Next critical point is your at length L. We want to say what is the value of shear force at value at L. We can write that the from the equation that dV by dx equals to V, dV by dx equals to V W. Then we have that V2 minus V1 equals to loading area of the loading diagram. Area of the loading diagram. So your shear force 2, that means shear force at L, we can write shear force at L minus shear force 1 was your 0 at the supports, and then equals to area of that loading diagram. Half of loading is acting downwards minus WL. That means shear force equals to minus WL by 2. So downwards the minus WL by 2. So it's your minus WL by 2. Minus WL by 2. Now since the loading here is 0, at the mid loading is 0. If you write if the loading is 0 at the mid, that means slope is also 0 at the mid. So slope is also 0 at the mid. And since at the supports there was a loading intensity of W, so you have a slope of W but minus W. Because loading is downwards, so you have minus W. So now now you have to join the 2 points. Since the loading is 1 degree, you can have a 2 degree parabolic curve between the 2 points. Say this one. And similarly, for the next part, you can also have the shear force diagram such that it would become finally 0. Let's try to verify it. Say the shear force at length 2L. We can say shear force at length 2L minus shear force at length L equals to area of the SFD. That is equals to since the loading is acting upwards, loading is below the line, it does not make any difference, but the loading is acting upwards, so your loading is positive. We can write the loading is positive WL. So we can write V2L equals to 1 by 2 WL minus times plus times VL. VL is your minus WL by 2. So your final shear force becomes 0. And the slope here is 0, but the slope here, it has to be equals to W but positive. So we have the positive slope of that plus positive W. This is your SFD. Negative. Final diagram is your negative SFD. And both sides are 2 degree parabolic. Now we have to make the SFD, that BMD. We have that at the cantilever side, we have the moment A that was equals to 2 by 3 WL square. That was clockwise. That clockwise moment is positive for BMD. So we know that we have if the moment is acting positive, this clockwise, we have that sagging moment. So your bending moment diagram is positive 2 by 3 WL square. So your value of BMD at the support, and this support cantilever side, it's equals to 2 by 3 WL square. Now see the slope here, it has to be 0 because your shear force is 0 at the point, at the starting point. So your BMD has to be 0, but the shear force here, shear force at the mid, it is not 0. So your slope at the mid is not 0. But we say that the shear force, since your shear force diagram, since V is shear force is decreasing, shear force is, we can write that shear force is negative and decreasing. and increasing, we can see that shear force is negative, but it is increasing in value. So we can say that moment is BMD, moments BMD, we can write that BMD slope, BMD slope is also BMD slope is also negative and increasing. BMD slope is also negative and increasing. Say since initially there was a moment of 2 by 3 WL square, and the BMD is negative, BMD slope has to be negative. For the starting point, BMD's slope is 0, but BMD slope has to be negative. That means at any point mid there has to be a negative slope, and the slope is has to be a decreasing. It has to be in the form of increasing. That's from 0 to some slope. Let's say what is the value of that slope. We would calculate. We would check the value of bending moment at mid first. Say the bending moment at mid, we can calculate that. Let's say this is up to the mid part. We want to calculate the bending moment at mid. Say the shear force here is V, and the bending moment here is moment at mid, and the moment at A was equals to clockwise 2 by 3 WL square, and the shear force and the reaction at A was 0, and we know that the shear force at the mid was your WL by 2. Shear force at the mid is WL by 2. We can directly say that shear force here is WL by 2, but it has to be upwards. It has to be upwards because this one is downwards. So final shear force, it has to be upwards, WL by 2. Let's say the moments at, we can say that moment at mid, we can calculate summation of moments at mid equals to 0. So your minus anti-clockwise, that your clockwise moment of 2 by 3 WL square, and your UDL of intensity W at the at the fixed support, and the length is L. We can calculate the effect at anti-clockwise. That means that 1 by 2 W into L acting at a distance of 12 by 3, and your moment M mid anti-clockwise direction, moment at mid goes to 0. Then we uh, shift it, and we can write M mid equals to this value. So your final value of mid, moment at mid, comes out to be uh, 2 by 3 minus 2 by 3 minus you have 1 by 3. That means your moment of positive moment of WL squared by 3 is your moment at mid. WL squared by 3. Actually, initially there was a moment of 2 by 3. Now you got 1 by 3. So you got WL squared by 3 BMD value. Then we had to connect in the 2 points in this way, that BMD slope is negative and increasing. BMD slope is negative. Here the BMD slope is 0. Here the BMD slope is negative and increasing. So your value is increasing from 0 to your to some value. That value of slope is, that slope value is, okay, right, tan theta equals to minus times your WL by 2. That's equals to shear force at this point, that is minus WL by 2. That's why it's negative, but it's increasing. It's increasing because shear force is increasing from 0 to L, and shear force is increasing as we move from 0 to L. Similarly, BMD slope would increase from 0 to L. So you got the values of BMD points, two critical points. Now we need to get the value of BMD at bending moment value at the end, we can say that uh, let's say we got the value of bending moment value at mid equals to WL square by 3. Let's say, since we know the bending moment is the summation of all the moments from either side of the section. If you cut the section at mid, say you got a moment of uh, WL square by 3 in this direction, that means for this side it would be a moment of WL square by 3 in the opposite direction. So if we have this section now, your intensity is W or length L, and your moment here is uh, clockwise moment of WL square by 3. And your shear force was that at the mid part, your shear force was, let's say here the shear force was upwards, here the shear force would be downwards, WL by 2. Let's try to calculate. Want to calculate the moment at your free end. We know that moment at free end has to be 0. We can also check it. Say your say moment at, say we want to say what is the moment at the end. Moment at end, we can say summation of moments at end equals to 0. We can write WL square by 3 clockwise plus minus times WL by 2 into L, and your loading intensity of clockwise 1 by 2 WL acting at L by 3 minus M end goes to 0. That comes out to be 0. So you have the BMD value, bending moment value here 0. Here we have WL square by 3. You have to join the 2 points. There is no critical point between the two, so there won't be any sudden change in the path. So we have that at the mid part. We have the slope. Equals to WL square by 2 negative. So but for the next part, we have that we can write that for the if see in the part, let's say it is your part C, and let's say it is your part CB. In If in the CB shear force is shear force slope is increasing. Now shear force value is increasing. We can say shear force slope is positive, and that means shear force itself is is mm, we can say that shear force is negative and increasing. We can write that we can write shear force is negative and decreasing. So your BMD slope is negative and decreasing. So your slope here is 0. And the slope here is some value of minus WL by 2. So you have to join the two. This is a curve of degree 3. Yeah, 3-degree curve, cubic. This one is also 3-degree, but the variation here was this way. The slope here was 0, and here was something, and here is something slope. It is not 0. There is some slope here, and the slope here is 0. So this is your BMD, like this one. Say this way. and after that this one. I think we should end the class for now. Thanks for watching our strength of material. Thanks to everyone.